Okay, let's unpack this deep dive. We're looking at Class D amplifiers today,
Right.
and specifically how this tech made a huge leap. I mean, it used to be just for subwoofers, kind of
Yeah,
niche.
exactly. Low frequency stuff.
And now it's basically the standard for high fidelity, full range audio. So, our mission really is to figure out the physics, the breakthroughs. What actually made that happen?
Well, it really all comes down to one core thing.
Yeah.
Efficiency. It's a completely different approach compared to, say, traditional linear amps, like Class AB.
Okay.
Those amps, they operate in what's called the resistive region. So they're always kind of on, and they waste a lot of power.
Just burning it off as heat?
Pretty much. You're looking at maybe, 35 to 50% of the power just becoming waste heat.
Mm-hmm.
Class AB might hit 50, maybe 65% efficiency if you're lucky.
Mm-hmm.
But Class D, it's different. It acts like a switch. Think digital.
Mm-hmm.
It's either fully on or fully off-F, usually using MOSFETs to do the switching.
Ah, so you're cutting out that middle ground where all the energy gets wasted.
Exactly. You eliminate that time spent in the inefficient zone. And the numbers, well, they speak for themselves. You jump from maybe 50, 60% efficiency.
To over 90% with Class D? That's huge.
It is. And think about the thermal impact. Less waste heat means less heat to get rid of. A 90% efficient Class D amp makes only about 1/5 the heat of a 50% efficient Class AB one.
1/5. So that explains why they're so much smaller. You don't need those massive, heavy heat sinks anymore, or maybe none at all sometimes.
That's the geometric advantage, yeah. It makes them practical, portable. You can put them anywhere. That change was critical.
Okay, if they're so efficient, hitting 90% plus, why not 100? What's happening with that last, 5 or 10%? Where's that inefficiency coming from?
Good question. It's not perfect, you're right.
Yeah.
That remaining loss, it mainly boils down to two things happening in the MOSFET switches themselves.
Okay.
First, there's conduction loss. That's just basic electrical resistance when the switch is fully on. We call it RDS on. There's always a little resistance.
Makes sense, like friction.
Sort of, yeah. And second, and this one's trickier, is switching loss. This depends on how fast you're actually flipping that switch, the switching frequency, F sped UW, and also the energy needed to turn the switch on and off, the gate charge or QG.
Right, and here's the conflict I see coming. For really good audio, high-fidelity sound, you need the full range, right? 20 hertz all the way up to 20 kilohertz.
Yep, the full human hearing range.
To reproduce that cleanly with a switching amp, don't you need to switch really fast? Like hundreds of kilohertz, way above the actual audio frequencies.
Exactly. You have to push the switching frequency way up high so the switching noise itself is way outside what we can hear. But see the problem.
Yeah, the faster you switch, the more that switching loss you mentioned comes into play. Power loss goes up with frequency.
Precisely. So back in the early days, you had this fundamental trade-off. You could have amazing efficiency, or you could have high-fidelity sound. But getting both was really, really hard. You increase frequency for fidelity, you lose efficiency.
So how did they crack that? Because early Class D amps didn't sound great, did they? Lots of distortion.
No, they didn't. The distortion was a major issue. One big part of fixing that was tackling something called dead time.
Dead time.
Yeah, you need a tiny, tiny gap when you switch. You can't have both the high side and low side switches on at the exact same minute, or you get a short circuit shoot through, which basically blows up the device.
Catastrophic failure. Okay.
Right. So you need this non-overlap period, this dead time. But that necessary pause, it introduces timing errors. And those errors directly create distortion in the audio output.
Okay, so how do you fix an error that you need to have?
Well, with cleverness. Modern designs use really sophisticated high-speed feedback loops and digital signal processing, DSP. They essentially measure the error caused by the dead time and aptly compensate for it, correcting the output waveform in real time.
Smart. So feedback and digital processing cleaned up the signal quality. But we still have that switching loss problem, right? Switch faster, lose more power. How'd they get around that? Was it new materials?
That's exactly where the next huge breakthrough came in. Gallium nitride. GaN, right. I've heard about that. How does it help here?
GaN transistors, specifically GaN HEMTs, have this amazing property. They virtually eliminate something called the reverse recovery charge, or QRRR.
QRR, okay, what was that doing?
In traditional silicon MOSFETs, that reverse recovery charge was a massive headache. Every single time the switch turned off, this charge caused ringing, noise electromagnetic interference, or EMI, and just generated extra heat. It was a primary source of switching noise and loss.
Wow, so GaN just gets rid of that problem.
Pretty much. By removing that QR issue, GaN basically gave designers the freedom to crank up the switching frequency, get that high-fidelity audio resolution, without the huge penalty in noise and heat loss they used to pay with silicon.
That's a game changer. A new material just bypasses a fundamental limitation. But you mentioned architecture, too, not just materials. Absolutely. Materials were key, but so was smarter design. Things like proprietary multi-level modulation techniques. Instead of just switching between 2 levels on N and OFF, maybe you switch between 3 or 5 levels.
How does adding more levels help?
It makes the output waveform, that switched waveform, a much closer approximation of the actual audio signal you want. It's a smoother output before filtering. This reduces the remaining ripple, the high-frequency noise, dramatically. We're talking maybe up to 10 times less power dissipation in the output stage.
10 times less power, that's significant.
It is, and it has a huge economic impact too. Because the output is already much cleaner, you don't need those big, complex, expensive LC filters on the output anymore.
The inductor capacitor filters.
Yeah, those can be bulky and costly. With multi-level modulation, you can often just use simple, tiny, cheap ferrite beads instead, so it shrinks the size and the cost.
So better material with GaN lets you switch fast without penalties, and smarter architecture, like multi-level, makes the output cleaner and cheaper to filter. That's quite a combo.
It really is. Those two things together are what truly enabled high-fidelity Class D.
So bringing it back to the listener, to you listening now, why is this dominance of Class D actually important in our daily lives?
Well, it's everywhere now, and for good reason. Think about portable devices, phones, Bluetooth speakers. Class D is basically mandatory there. That efficiency boost. It can extend battery life by like 2.5 times compared to older amp types.
Huge for anything battery-powered.
Definitely. And then look at cars, the automotive world. You're seeing audio systems now pushing over 1,000 watts RMS.
1,000 watts in a car.
Yeah. And Class D's efficiency is what makes that feasible on a standard 12-volt car electrical system without, melting the wiring or needing a second alternator. It just draws less current for the same output power.
So the efficiency isn't just about saving power, it enables higher power in constrained environments.
Exactly. So you look at the whole picture, the efficiency, the size reduction from less heat thanks to GaN, the cost reduction from things like multi-level architectures. The technical and economic case for switching amps is just undeniable now.
It really seems like Class D has completely won.
It has, for most applications.
Yeah.
Which leads to, I think, the really interesting question going forward. Well, we've established that switching is superior. We've seen how GaN and new architectures drastically cut down the heat and the space needed. So if those massive heat sinks aren't the main limitation anymore, how far can we actually push power density? How much power can we pack into an even smaller space now that heat isn't the absolute bottleneck it used to be? That's the next frontier, I think.